So this lesson is on calculating pH or pOH. What do you think pOH is about? Hydroxide ion. So it's like measuring bases, right? Like how strong a base is. And pH is measuring kind of how strong an acid is. Okay. What do you think the P and the H stands for? Have you ever? Power of hydrogen. Yes, yeah. That's what it stands for. And now, you're going to have to remember back to some sig-dig rules we did. Normally, all of our sig-dig rules focused around when we multiply or divide numbers, because most of our questions were doing at least one of those. But with these ones, you will be doing adding and subtracting. So with pH and pOH, you have to use adding, subtracting sig-digs. So I'll review those with you too. So just keep that in mind that your sig-digs will need to be different for this, for pH and pOH usually. So when we're thinking about pH and pOH, first we need to look at water. Now water actually kind of self-ionizes, but it's a very small amount. Only like 2 waters in 1 billion will ionize. So if I have liquid water plus a liquid water, because really to have that ionization you have to have the reaction with water, it will make H3O plus. So if I took like a hydrogen from here and I added it onto this one to make that, what's left over here?
H.
Yeah, or OH, yeah. So this is why water is thought of almost too as neutral, because it can do both, okay? Now, the concentration of hydronium ions and hydroxide ions are equal. So hydronium ions and hydroxide ions are equal and constant in pure water. So that's why their pH is 7. So that's our reference point. So now, when we look at H3O plus here, when anything is in square brackets, that means concentration. Okay, really important. So anything in square brackets, that means concentration. Not like concentrate on this hard, like concentration as in, moles per liter or something. That was a joke. At least my attempt at one. Okay, so this is saying our concentration of hydroxide or hydronium ions in water is 1.0 times 10 to the power of -7 moles per liter. Okay, if you took water, and you can't have a different concentration of water, right? Because water is water. You know, when we think about concentrations, it's dissolved in water. Well, it's just water, okay? And then OH, if it's equal and same to it, it's also 1.0 times 10 to the -7 moles per liter. Now, do you see a number that is familiar from properties of water? What's the pH of water? 7. Oh. Curious. There's 7s there. It's not a coincidence. I'll show you why. It all starts with the pH scale. With Søren Sørensen. He devised the pH scale. It is used because the hydronium ion is very small. So when we're looking at our concentrations, it's annoying to say, 1.0 times 10 to the power of 7 moles per liter. So we have a different system for that. So at 25 degrees Celsius, most solutions have a pH that fall between 0 and 14. Now, the pH scale can go above 14 and it can go below 0. Did you know that? It can. There is things that have more basic, than this and more acidic than this. But most fall within this scale. That's why we always draw it like that. But if you get an answer that's above or below that, it's not wrong. Okay? Well, it might be, but not just because it's over on the scale. It is possible to have a negative pH and a pH above 14. It's just not common. It is a logarithmic scale. So using a function of log. Okay? So logarithmic scale based on whole numbers that are powers of 10. This is where it gets exciting. If you take like calculus, you'll understand logarithmic scales so much more, and then you'll be like, whoa, everything connects. At least that's what I thought when I took it. Okay, so there is a 10-fold change in hydronium ions for every change in 1 on the pH scale. This is really, really important that you probably memorize this, because when you get a question like this on a test, you're just going to think it's by 1, but it's not. It's by 10, because it's a logarithmic scale, so it all changes to the power of 10 at every unit went up. So we'll do an example where you see this. So a solution, say, with a pH of 11 is 10 times 10 equals 100 times more basic than the solution with a pH of 9. So it's like if, I wonder if I drew it. So here, if I have my pH scale from 0 to 14, that's more basic, this is more acidic, that is neutral. So what happened, I'll just wait a minute. So this question is saying, so like if you got this on a test or something, this is how it would be worded. If you have something, what is each of these? How does it go up by? Whatever, I'm just going to put a 9 there, okay? If you had a pH of 9 and a pH of 11, how many more times more basic is the 11 solution than the 9? Well, in between here was 10, so you need to think here to here is 10, here to here is 10. 10 times 10 is equal to 100 times more basic, okay? Because, then the reason for that is because it is a logarithmic scale, okay? Each one goes up by 10. See that? Don't forget it. Important. Just put a star beside that. Like beside this. So, when you have to calculate pH and pOH, you can convert between, like if you get your moles per liter, you can convert that into pH and pOH. I'm just going to start a new video.